Hello, good day to each and everyone. My topic is all about work kinetic energy or work energy theorem. So, what is work in kinetic energy? Basically, it is also known as the work energy theorem. It is a form of energy in which an object or a particle has by reason of its motion. It is also a property of a moving object or particle and depends not only on its motion but also on its mass. If work, which transfers energy, is done on an object by applying a net force, the objects speed up and thereby gains kinetic energy. The kind of motion may be translation or motion along a path from one place to another, rotation about an axis, vibration, or any combination of motions. Translational kinetic energy of a body is equal to one half of the product of its mass, symbol letter small m, and the square of its velocity, symbol letter small v rather, or one half mass times velocity squared. This formula is valid only for low to relatively high speeds. For extremely high speed particles, it yields values that are too small. When the speed of an object approaches that of light 3 times 10 to the power of 8 meters per second or 186,000 miles per second, its mass increases and the laws of relativity must be used. Relativistic kinetic energy is equal to the increase of the mass of a particle over that which it has at rest multiplied by the square of the speed of light. The unit of energy in the meter kilogram second system is the joule. A 2 kilogram mass, something weighing 4.4 pounds on Earth, moving at a speed of 1 meter per second, slightly more than 2 miles per hour, has a kinetic energy of 1 joule. In the centimeter gram second system, the unit of energy is the ERG, or we can call it erg, 10 to the power of negative 17 joule, equivalent to the kinetic energy of a mosquito in flight. Other units of energy also are used in specific contexts, such as the still smaller unit, the electron volt, on the atomic and subatomic scale. For a rotating body, the moment of inertia, symbol of big letter I, corresponds to mass, and the angular velocity omega, symbol of the omega, is this one, corresponds to linear or translational velocity. Accordingly, rotational kinetic energy is equal to one half of the product of the moment of inertia and the square of the angular velocity, or one half moment of inertia times omega. No. One half moment of inertia times velocity squared. Note that the total kinetic energy of a body or a system is equal to the sum of the kinetic energies resulting from each type of motion. I'll be showing a sample video presentation on how to solve work kinetic energy or work energy theorem.
If you are in motion, if an object is in motion, then you have kinetic energy. The equation symbol for kinetic energy is KE. I think this is the one you see most often, KE, but you might also see this E like energy kinetic, like you might see EP for energy potential. But I think either kinetic energy, KE, that's what I tend to use, or EK, kinetic energy, kinetic. Remember the SI unit, the unit for kinetic energy, potential energy, all energy and work and heat and all that stuff is the joule. James Prescott Joule, Joule, abbreviation J. This is the equation that we used. You've probably seen this before. Kinetic energy is equal to 1/2 times m times v squared. Remember, we'll talk about this again, but it's just the v squared, not mv squared. It doesn't matter the order in which you do these things in your calculator. Remember, the mass must be in kilograms. M is for the mass. If it's given in grams, you have to convert first to kilograms. And don't forget the velocity needs to be in meters per second. V velocity meters per second. 1/2 mv squared. You can see all objects, in order to have kinetic energy, they have to have some motion. Sometimes we say velocity, sometimes we say speed, but it's technically speaking, you're supposed to say velocity. But here we go with the speed. And here's one of our examples. A car is moving down the street, the road, with a speed of 20 meters per second. If the car, it's kind of a small car, has a mass of 600 kilograms, how much kinetic energy does the car have? Well, here's our equation. It's pretty straightforward. We're just going to use this equation the way it is. No rearranging, solving, plug the numbers in. Now I like to write down 0.5 and 1/2 is the same thing. The mass 600 kilograms. The speed we said was 20 meters per second, and we're going to square the 20 meters per second. Don't forget that, and you will get that's actually 120,000 joules, which might be better for significant figures if we wrote 1.2 times 10 to the 5 joules. Now, one of the most interesting things is with kinetic energy, of course, is what happens if we double the velocity. So we're going to do twice the velocity. When the speed, if the speed is doubled, what is going to happen to the kinetic energy? Is it going to go up? Is it going to go down? Or is it going to stay the same or something else? So let's just check it out. We can calculate it really quickly. 0.5, 640, so we double the velocity, double the speed, but remember, it's double the speed squared, so it's like doubling the double. And so the kinetic energy is not going to just be 240,000, because we're doubling and then we're squaring. It's going to be 4 times as much. You can see that this value, 480 times, is 4,000. 4,000 is 4 times this value of 120,000 joules. So please don't forget that. Okay, when you double the velocity, you quadruple the kinetic energy. That's why when you're driving a car, if you're going really fast, you can hurt yourself because it takes twice as much work. 4 times as much work. Why did I say twice? 4 times as much work to stop, or energy to stop you. So be careful, and don't forget, it's not just velocity, but it's velocity squared. It's 4 times as much. Okay. Here's the next one. It's a girl. She's riding her bike, and she has a speed of 5 meters per second. And her kinetic energy, her and her bike together, they have a kinetic energy of 550 joules. And we want to know what is the mass of the girl and the bike together. Here's our equation. Now this time we want to solve for the mass. We got to solve for the mass, so we got to get rid of these other things over to the other side, so to speak. And the easiest way to do it, now there are more than one way to do this. But the easy way, I always tell my students, when I see a 1/2 here, a 1/2 mv squared, where else do we see a 1/2? I can't remember it right now. But 1/2, the easiest thing to do is just to multiply by 2. So I make this little line. I'm going to multiply both sides of the equation by 2. So I get 2 ke. Ke times 2 is 2 ke, and 1/2 times 2 is 1. So we lose the 1/2. Get rid of the 1/2, which is what we want to do. We move it to the other side and just mv squared. Now we want to know the mass, so we got to get rid of the velocity squared. So now we're going to divide by velocity squared. When we divide by velocity squared, we get that the mass is equal to 2 ke divided by the velocity squared. We're given the ke. It's 2 times 550, and the velocity squared. Remember, once again, you guys square the velocity. This is 5 times 5 is 25. So this is 1100 divided by 25, and you get that the girl and her bike have a mass of 44 kilograms, just like that. Okay, and the next one is we have Billy, and he's going to drop a rock with a mass of 0.45 kilograms. He's going to drop that from a cliff into the lake below, and it has kinetic energy. The rock just before it hits the water is 140 joules, and we want to know what is the speed or what is the velocity of the rock just before it hits the water, not when it's sitting there at the bottom of the lake, but just before it hits the water. So now we're going to take our same equation, and this time we want to solve for the velocity. Now this is a little bit more complicated. Okay, now remember in the potential energy video we used the magic math triangle, and you could technically do that for the magic math triangle for this case for kinetic energy, but the mathematics and the math is a little bit more unconventional and a little bit more messy, so to speak. But we're just going to do this is a good way to practice your algebra. We're going to multiply by 2 again, same thing. Now here we have the same equation we had in the previous example, but now we don't want to solve for the mass, we want to solve for the velocity squared. So we're going to move the mass over to the other side by dividing by the mass, and now we have that the velocity squared is 2 times the kinetic energy divided by the mass. But we don't want to know the velocity squared, we want to know the velocity. So in order to get rid of the velocity squared, or get rid of the squared, we're going to take the square root of both sides. When we do one thing on one side, we got to do the same thing to the other side. And you can see that if I take the square root of v squared is just v, but then I got to take the square root of 2 times ke divided by m, which I can now just plug the values in. Square root of 2 times 140 divided by 0.45 kilograms. There's nothing to square here because we got rid of that with our square root. And then we find out that the speed of the rock, the velocity of the rock, just before it hits the water is, I think I did in my calculator, I got 24.9 something, I rounded to 25. So therefore we have our 2 significant figures, and we have 25 meters per second. So there you go, that is kinetic energy. That's actually translational kinetic energy, not rotational or some other kind of kinetic energy. That's translational kinetic energy, and that's usually, the simplest kind of kinetic energy that we're usually talking about. So thanks for watching. Hope you found it very helpful. If you did, please do all of the following